Okay, so we are going to start our chapter 9. This is chapter 9.1. And just these are some of the things that we're going to talk about in chapter 9. We're going to talk about Newton's law of universal gravity, applications of gravity. We're going to talk about circular motion, which is different from what we just finished talking about with rotary motion. And then lastly, we're going to wrap it up with the motion of the planets and orbits. Okay, so let's move this up here. All right, so remember, gravity is a force of nature that attracts one mass to another. So we usually think of it in terms of the fact that we are attracted to the surface of the Earth. That's why we can't float around. So we are one mass, the Earth is another mass, and so gravity is just our attraction of one mass for another. And that's just the example of us and the Earth. Gravity holds you on the Earth. It causes apples to fall to the ground. It accelerates you as you're going downhill because you're getting closer to the surface of the Earth. So that's some examples that we come across with gravity. Oops, back. But if we think about it on a much larger scale, if we think about it in terms of the universe, not just us and the Earth, but the entire universe, the same applies. Okay, so gravity is responsible for the motion of the moon, the Earth, and all the planets. It's what keeps everything in its place. Okay, so we have a force of gravity of every object for every other object. Okay, and that's basically Newton's law, universal law of gravitation. So the force of gravity between any two objects, no matter what they are, mass 1 and mass 2, separated by a particular distance r, is attractive and has a magnitude of F, force of gravity, given by this equation. Okay, so where F is our force of gravity, capital G is a constant, not 9.8. It's a different constant. Okay, and M1 and M2 are the masses, and the distance between those two masses is expressed as r. Okay, so that is Newton's universal law of gravitation, or the formula for determining that. The constant capital G is given by this number right here. Okay, that is the universal constant, gravitational constant G. So all objects in the universe attract all other objects in the universe. So everything in the universe has an attraction for or feels everything else. Okay, so as you see in the figure below, Newton's law of gravitation states that the force between two masses is directed along a line connecting those two masses together. Both masses in the figure experience an attractive force of the same magnitude. And it's given by that formula that we just saw. The force of gravity between those two objects form what's called an action-reaction pair. So M1 is attracted to M2. So M1, the force of gravity for M1 acts in one direction, and the force of gravity for M2 acts in the opposite direction. That's why it would be an action-reaction pair along that distance r that is separating those two objects. So G is a very, very small number. Capital G is a very, very small number. So this force of gravity is extremely weak. It's one of the weakest forces of nature. The force of gravity between objects of everyday size is pretty much imperceptible. You're not really going to feel it. It only becomes important when we talk about very large objects like planets and stars. Okay. All right, so here is an example problem. The example below illustrates how Newton's law of gravity may be applied. Note that the gravity's minuscule effect on ordinary objects. So all of your numbers when we're dealing with ordinary objects, this force number is going to be tiny, tiny, tiny. Very, very, very tiny. So a girl takes her dog for a walk on a sunny beach as shown below. Find the force of gravity between this 45-kilogram girl and her 11-kilogram dog when they are separated by a distance of 1 meter. Treat the dog and her girl, or the girl and her dog, as point masses. So here's the girl, here's the 1 meter leash, here's the dog. Okay. And so the girl has your 45-kilogram mass here. Your dog is M2, that's 11 kilograms. The distance between them is 1 meter. So we're going to square that. We're going to multiply it by the constant G, which is, again, a tiny, tiny number. So when we do that, we should get a really small number. So the force of gravity between the two of them is 3.3 times 10 to the negative 8. So unless you're talking about planets and stars and that kind of thing, all your force of gravity numbers should be pretty small. All right. Gravity decreases with the inverse square of the distance. So if you think back to the formula, F equals m1 m2 over r squared, okay? So that's what we're talking about here, and that's why this graph, if we plot force of gravity versus the r, it's going to drop off dramatically because that's the inverse square. It's an inverse square relationship. Because of this, we say that gravity obeys an inverse square force law. Even though the force of gravity diminishes rapidly with distance, it never completely goes away. So gravity has an infinite range. You are always going to have gravity. That's all that means. We can't just get away from it or get rid of it or whatever. There's always going to be a tiny, tiny little bit. So if you think about it mathematically, when we have an exponential graph like that, we never actually reach the 0 point. We just keep going and going and going forever without ever reaching 0. And that's what they mean by an infinite range there. Oops. Okay. So here's a conceptual example, and a lot of times those are the ones that really kind of get us because we have to really think about those. We can't just plug into a formula. If a mass experiences gravitational forces from a number of other masses, then the total force acting on it is the vector sum of all those individual forces. So remember, we're talking about a force which is a vector quantity. And then you're just going to add up all of those vectors with their directions, okay? The fact that the forces of gravity add together like vectors is also referred to as superposition. So we're going to add them up as a vector, not just as just the magnitudes, okay? So here's the example. Each of the 3 equally spaced and equally massive objects shown below experience gravitational force due to the other 2 objects. Rank the objects in order of increasing magnitude of the total gravitational force they experience. Indicate ties where appropriate. So we have point A, B, and C. We have mass A, B, and C, and we want to know what's the total force of gravity experienced by one object from the other 2. The total force acting on object A is toward the right. The total force acting on object C is towards the left. Because the symmetry of the 2 systems, the magnitudes of these 2 forces are the same. The magnitudes of these 2 total forces are the same. The total force acting on object B is different. Object B is attracted equally to the left and to the right. So object A is only attracted in this direction. Object C is only attracted in that direction because there's nothing on the other side of it. But object B is attracted in both directions. Okay, so object B is attracted equally to object A and object C. So these attractive forces cancel out, leaving a total force of 0 acting on object B. So the way you would rank it is that B is going to have the smallest force because it's 0, because its force gets canceled out because you got one going in one direction and one going in the exact opposite direction. So they wind up canceling out. So B is 0. So that obviously is going to be less than A. Okay. And then A and C are going to wind up being equal because they're the same mass, they're acting in opposite directions. So A is pulling is pulling towards the left, B is pulling towards, no, I said that backwards, sorry. A is pulling towards the right, B is pulling towards the left, and so those two forces are going to come out to be equal. They're not going to cancel out because they're not going in opposite directions. Okay, so hopefully you can see from my little diagrams here that these are going towards the same direction, towards the same point. Okay, so they're going to be equal forces. But here, that attraction is going in the opposite direction, so it cancels out. Okay, all right. Any object sets up a gravitational force field that extends from one end of the universe to the other. The visual representation of the Earth's gravitational force field is shown in that figure. So it's just showing you kind of using arrows and vectors what direction gravity is acting. Obviously, gravity is acting straight down towards the Earth at every point on the Earth. Okay. And so we call that the gravitational force field because it's all the way around the Earth at every particular point on the Earth. The force vectors point towards the Earth's surface, and they become shorter in length as the distance from the Earth increases. So that ought to make sense. The higher above the Earth we go, the less gravitational force we experience or pull we experience. So these vector arrows need to get smaller and smaller the further we get. And the closer we get to the Earth, then those vector arrows will become larger and larger because the magnitude of our force is becoming larger and larger the closer we get to the Earth's surface. And that magnitude of that gravitational force is becoming smaller the further away we get from the Earth's surface. All right, I think that is it for 9.1. I believe applications of gravity comes in 9.2. Let me double check that. Yes. All right, so we will talk about applications of gravity next time. Make sure you let the video completely play out for the Edpuzzle so that it records your answers and that gets recorded in Schoology. All right, have a great day. If you have any questions, make sure you bring them to class. We'll be working on the exercises for 9.1 in class tomorrow.